Okay, welcome back. I see lots of people didn't come. Okay. Now I switch to somewhat more complicated topics regarding the high energy bounds on graviton mediated scattering and corresponding implications for positivity bounds and EFT properties. Also, my purpose here is to show eikonal resummation technique and the way of how analog of Martin-Froissart bound can be got from this kind of technique applied to graviton scattering. Unfortunately, it doesn't work in 4 dimensions, but in D dimensions, for the sake of showing how could it work. So I will illustrate this derivation and show what are the problems with the 4-dimensional graviton scattering amplitude. Why it doesn't seem to be easy to get a local version of some non-perturbative amplitude. Okay, let me start maybe from extension of partial wave expansion to D dimensions. We did everything in 4 dimensions. It was related to Legendre polynomials. In D dimensions, the proper functions are called Gegenbauer polynomials. So the analog of partial waves in D dimension, I would define D-dimensional Legendre polynomials. And that's the expression for them. So this is some normalization factor, which I'll write later. D-dimensional Legendre polynomial can be written through the so-called Gegenbauer polynomial. Let me write it. So the function playing the role of basis for partial waves, PL of D of Z, can be expressed through the known special functions, which as a factor gamma of 1 plus L, gamma function of D minus 3 over gamma of L plus D minus 3, and CL of D minus 3 over 2 of Z is a Gegenbauer polynomial. Their properties can be found in any textbooks on orthogonal polynomial systems, special functions, and so on. They are just another type of polynomials which are orthogonal with respect to somewhat different function, such that our D-dimensional polynomials which we are using for partial waves, they are normalized by the condition 1 minus with a factor 1 minus z squared to the power d minus 4 over 2 delta LL prime over n of d factor and normalization factor n of L and d. And these are just numbers. N of d is 16 pi to power 2 minus d over 2 over gamma of d minus 2 over 2. And normalization factor of n of LD is 4 pi to d over 2. Sorry, there are quite many quite annoying numerical factors. It would be much easier to use some supernatural units, as someone told me, like pi equal to 1. But there are dependencies on number of dimensions and some other factors. So it's some combination of gamma functions, gamma of d minus 2 over 2, and gamma of L plus 1. So there are some normalization factors which are somewhat different from 4-dimensional life. And in d dimensions, we have a polynomial system which is normalized such that it's an orthogonal polynomial system with function 1 minus z squared to the proper power, which depends on number of space-time dimensions. These are just eigenfunctions of momentum operator in d dimensions. Yes.
So where is this d-dimensional information hidden in the amplitude that requires you to use these functions and not the normal Legendre ones?
It's encoded such that, well, in the final form of the amplitude, it's not seen anywhere at all. It will be seen when you, for example, in the technique I applied for computing one loop, it is very strictly a 4-dimensional technique. Because I used partial wave unitarity, full partial, like elastic unitarity of partial waves. And if I do it in another dimension, then the coefficients, I have to expand everything with respect to these new polynomials, and I will get different result. Moreover, I'll get not logarithm of t, but probably in 5 dimensions, it should be some root t, square root of t, singularity appearing in the loops. So the life will be a bit different if I go to other dimension.
Just if you can remind me, in the 4D case, was there an exponential that you expand? Like there was an exponential that you expanded, or what was the origin of the Legendre polynomials in the 4D case?
The origin was all of these polynomials appear as eigenfunctions of momentum operator. You just solve equation in spherical harmonics, which are different, depend on dimensions. In 4 dimensions, it corresponds to special functions related to Legendre polynomials. In other number of dimensions, momentum operator has you have another equation which you need to solve
So
to find the corresponding.
I understand it from a space point of view, yes. But so okay, what I mean is the argument of the Legendre polynomial was a cosine theta, which actually was this quantity.
Yeah.
But that theta actually was that theta the actual scattering angle or just a parameter?
Actual scattering angle.
Oh, I see. Okay.
In d dimensions, this is also scattering angle, because two particles scatters in one plane, and it doesn't matter how many dimensions.
It's a physical angle in
Yes.
higher dimensions.
Yes. But the momentum operator has different set of eigenfunctions. That's why I need somewhat different dimension-dependent expansion. And of course, all the results can be rederived in d dimensions, like partial wave unitarity, but partial wave unitarity statements would be somewhat different. Optical theorem will get another somewhat different kinematical factors in higher dimensions. It will be imaginary part of FL is larger than s minus 4m squared to the power d minus 3 over 2 over root of s modulus of f L of s squared. And instead of partial waves less than 1, in d dimensions, it's like root s over s minus 4m squared to the power d minus 3 over 2. So that's new unitarity conditions valid for d dimensions. They contain d, and this is of order of s to for large s. What should it be? S to power minus d minus 3 over 2 plus 1/2 s to power 2 minus d over 2. I'll need this result later. And maybe for completeness of all these statements, let me also mention that apparently if we are dealing with not spinning particles, partial waves are not Legendre polynomials anymore. It should be Wigner D matrices. So they should take an information, have an information about helicities. So amplitude will be should be expanded into L plus 1 d L lambda mu of cosine theta, as I'm mentioning expansion of amplitudes, FL of H1, H2, H3, H4. And these are polarization states of the corresponding spinning particles like vectors or tensors. And here these corresponding values lambda should be H2 minus H1, change of helicity, and mu is H3, H4 minus H3. And these functions are somewhat differently defined polynomials. They can can in principle be expressed through Chebyshev polynomials, but in general, for practical use, if someone will be computing some stuff like this, it's called Wigner D function in Mathematica of 3 arguments like this. That's just some statement which might be useful for practical computations.
Is 4 to 4 is okay, no?
This is for d equal to 4, and in principle there could be also some. Well, I didn't search for this particular lectures the state like Wigner functions in d dimensions, but I'm pretty sure that it can be found somewhere.
So the one that we consider the main one with the Bagenbauer polynomials. What is the problem with d equal to 4? There is no divergence.
Sorry, not here. I'll come to this problem. It happens with graviton amplitude, graviton mediated. Yes. In general, there is no problem. It's very nice, very simple system of polynomials because you don't need this weight factor. But with gravitons, it's the same. So I mentioned all of this, especially this story, because one can make a mistake like using Legendre polynomials for scattering of vector particles, but it's not true. One has to be careful and look carefully into Wigner-D functions and use them properly. This moment we can try to solve the similar problem, like how to find the bound on this amplitude at low high energy. So can we get this squared or not, for example? Can we justify the use of positivity bounds, which require not faster than a squared growth, having this kind of amplitude? Because all the statements which I used for derivation of Martin-Froissart bound were based on massive particles and some analyticity properties which were expected, which certainly are not true if there are massless and especially gravitons. So in d dimensions, you can try obtaining the same statements with the use of techniques, with the use of similar techniques. We can try to split this sum to like A is like contribution of A low spins and estimate high spins. So let me come to the problem appearing with the gravitons. The problem, if we have a small t, now, and we will be also working in the case of it s going to infinity, small t. The problem appearing in 4 dimensions is related to the fact that if we compute FL of S, it will have a form 1 over d minus 4 L to power d minus 4, something like this. That will be S. So schematically, the problem is here because partial waves are getting divergent parts, 1 over d minus 4, and they depend on the spin as L to power d minus 4. That's why the life in higher than 4 dimensions is much easier, because at least partial waves are finite and there is no such a problem.
Which case this happen for graviton?
Graviton, yeah. The amplitude, if you take 3 amplitude, which is s squared over t, mp squared, you get this kind of behavior. That's why it's a bit tricky to repeat all the technique which I'll be explaining now exactly in 4 dimensions. Because here you have s over d minus 4 plus log L over me, something like this. And then one can claim that this is not relevant for something, but apparently it is difficult to justify the used approach. The reason is that in 4 dimensions, gravity is constructed such that it's very likely to have multi-particle events, like many soft gravitons emitted. So in total, the full cross-section, including emission of soft gravitons, will be still okay and finite, but amplitude is not a good quantity to measure it in 4 dimensions exactly. That's why it's hard to implement all these nice properties of analyticity and so on.
So if you take the amplitude A3 equal to S squared over
over T. Yes,
for dimension.
yes,
You want to expand it in a basis of Legendre polynomial.
yes.
You will not be able to do that because you have some divergent.
You get some divergent integrals, yes,
You cannot expand.
yes.
And in principle, can be accepted in principle the fact that we cannot expand it in Legendre polynomial, and we are fine with that.
Yeah, as I told that the reason behind it is that there are soft graviton emission which we cannot like see very easy because it's really kind of many soft graviton emitted, and this is likely to have this process. So it makes to the two amplitude some not very physical quantity in this case.
Also, the photon, that looks like the infrared divergence.
Yes, in photons it also happen, but in photons it's a renormalizable theory. You can do some cancellations first of all, and second, it doesn't affect dispersion relation techniques for the reason that photon amplitude is schematically S over T. And since we are interested in S² terms and all of this, graviton pole is spoiling many things. But photon, we don't care because we differentiate twice and it doesn't contribute anymore. So in D dimensions, the situation with the emission of soft gravitons is somewhat better. And in larger dimensions, it's even it's getting even better and better. So it could be a good approximation in higher dimensions to compute, to use elastic unitarity and compute amplitude, estimate at least as this, and estimate high spin contribution, high L contribution from elastic unitarity without inclusion of other emission of soft gravitons or so on. In D dimensions, it's a good approximation. And it still could be kind of relevant result because who knows, maybe we have, in fact, many like multi-dimensional space, like in string theory is suggested. So in fact, ultraviolet theory can have much more dimensions than infrared theory.
Divergence must be related to the divergence that you get also in the eikonal in 4 dimensions.
Yes, that's I'm gonna write the eikonal soon. In eikonal, indeed, you get these.
At the long range Newton potential.
Yes, that's true. I mean, in higher dimensions, it's a bit better. So this can be kind of, at least this technique can be written without divergences. So let me switch to explaining a bit what is eikonal technique and how it can be used. The idea is that eikonal resummation can be seen as unitarization of three-level graviton amplitude. Unitarization in the sense that we compute three-level partial waves and then assume that they are promoted to the phase of to the scattering phase, and the eventual the new partial waves of non-perturbative amplitude will be explicitly satisfying three-level unitarity, satisfying partial wave unitarity, and you can simply resum these partial waves and get full non-perturbative amplitude. Let me show how it works. The unitarity condition, this one, assume that to scattering is a dominant process, and we have elastic unitarity condition, which means that we have equality here. If we have equality here, then partial wave FL of S can be written as root S over S2 S minus 4m squared . Yeah, here for simplicity, I'm speaking about scattering of scalars through graviton. That's why I have massive particles like scalars, probably massive, but we consider they are light. Multiplied by I and by 1 minus exponent of 2I delta L of S, where delta L of S is scattering phase and it is real. So one can check that if this function, whatever it is just a real function, then partial wave will satisfy this unitarity condition. So the basic idea of unitarization of the amplitude is to take three-level amplitude, compute partial wave, promote it here, FL3 goes to scattering phase, and then improved partial wave, like as we believe it will correspond to some non-perturbatively resummed amplitude. The full partial wave will be standing in the exponent, and in order to obtain the answer for resummed amplitude, we need just to take this improved partial waves with three-level partial waves exponentiated here and get back the amplitude. And this approach is proved to work for large L, to estimate large L part, this one. And it's feasible to make this computation if one uses instead of momentum L, if one uses so-called impact parameter representation. So if there is a scattering center and we approach like this particle, this is B over 2, where B is an impact parameter. And the corresponding scattering momentum in this picture will be, this is particle with momentum P, spatial part of this momentum. We get that vector L is B multiplied by P. It's the physical interpretation how we get the relation between momentum and impact parameter. And apparently it will be B root S minus 4m squared over 2. And if m is 0, then it will be just B root S over 2. And at large momentum and large impact parameters, the theory we expected some kind of GR is a valid description. We are not dealing with we are dealing with large distances, but maybe even at high energies, GR is still good description in this case, because it's somewhat different expansion, large distances. So we'll be using like small mass and the limit like spin of the partial wave is proportional to B root S over 2. And impact parameter correspondingly is to L over root S. That's the relation between impact parameter and momentum of partial waves. Then in order to take these partial waves and resum them back to some candidate of non-perturbative amplitude, we need certain knowledge about d-dimensional Legendre polynomials, and the knowledge is like this. Yeah, and I will also use t equal to minus q squared. So the d-dimensional legendary polynomials at large L have the asymptotics of Bessel functions, actually. So we got some mathematical statement based on large L asymptotics of basically here Gegenbauer polynomials. It is related to Bessel functions, and for this reason, to perform resummation of partial waves, it is convenient to also write partial waves in terms of B parameter, impact parameter, which means that I will use the scattering phase coming as a partial wave of three-level graviton scattering amplitude, and the expression for it is gamma of d minus 4 over 2 can be written in terms of G Newton's constant S over pi to d minus 4 over 2 b to the power d minus 4. So again, the problem in 4 dimensions is visible here. And in addition, to simplify our life, we will, instead of the sum, we'll use integral root s over 2 L dB. We had sum with respect to L, and we can, using the relation between L and B, we can write it as an integral with respect to B. So then eikonal resummed amplitude will be equal to 2is to pi d minus 2 over 2. Integral starting from b star to infinity, dB, b to power d minus 3, bq to power 4 minus d over 2, Bessel function d minus 4 over 2, taken of bq, and we have the ansatz for the amplitude for the partial waves, which we are trying to resum. It will be exponent of 2i delta 3 of S and B. So this approximation, which works starting from some reasonable value of parameter B star, I will explain it a bit later. So B star should behave of order should behave as S to the power 1 minus D minus 2, 1 over D minus 2. This is the result from papers by Gabriele Veneziana, Amadici, Faloni. They derive this bound from the condition that at this when impact parameter is scaling like this with dimension, for lower B star, inelastic effects become important in this case. So we can trust this resummation that there is no extra emission of gravitons or some what they call tidal effects that are related to some already high energy scattering with small impact parameters, which cannot be described by GR, for example. But at impact parameters larger than the value scaling like this, we can use this resummation. So, and for this statement, I can refer to the paper Amati, Schiaffaloni, Veneziana of the year 1998. I found it quite the derivation quite complicated and going beyond the scope of these lectures. So I'll just use the result that the value of B from which eikonal resummation starts working will behave as S to power 1 over D minus 2. This will be essential for obtaining the bound. So this expression basically computes the sum over partial waves approximated as an integral of improved partial waves, improved and taken to the exponent. And this is a result valid starting from certain impact parameter. For lower impact parameters, it's much more difficult to obtain a good estimate of reasonable partial waves. And apparently, to obtain a bound on the total amplitude, we will do just estimation from. So we will estimate a low from the condition that FL is less than S to power 2 minus D over 2. It's I obtained it here. So it will be simple unitarity condition. And for also this is for B less than B star. Let me start from estimating a low spin contribution is proportional to sum of n of L and D, FL of S, PD, and modulus of this sum is of order of the sum from L equal to 0 to L star. And here I get the sum of n of L and D, S to power 2 minus D over 2, QL to the power 3 minus D over 2, S to power D minus 3 over 4. This mass is obtained because we have some property of Legendre polynomials in D dimensions of 1 minus 2q squared over S. They are always less than QL over root S to the power 3 minus D over 2. It's something which one can borrow from mathematical books. For example, for Legendre polynomials, I found it in Gradstein-Rizhik book, which collects a lot of formulas for special functions. So this is a property of special functions. And
which should be
Hmm?
the dimension, B is the length, S is the energy square. How do you map the dimension?
Yes. S is. So what was the
You have
question?
a B star,
Yes.
the order S to the minus, to the power 1 minus.
D minus 2.
Yeah.
D minus 2, yes.
B as dimension length.
Yes, but I'm caring about the factor of S here. Of course, it should be of dimension of the length. So
Which quantity you put in 15?
I think, well, should be something 1 over mass Planck, and it should be also over. I would do like this, but I need to check what exactly is standing there. But from dimensional analysis, I would expect that should be suppressed. It should be, there should be mass Planck everywhere because there is no other dimensional parameter. But of course, there could be numerical factors. So here I just directly substitute all these estimates. And I will be computing it up to L star. L star will be proportional to S to power D over 2D minus 2. If I just substitute how L star is behaving with B star, then I get this sum up to L star, and and it will be of order S to power 5 minus D over 4 L star to power D minus 1 over 2. Recall that N of LD is easily see it. So I think it can take some time recovering it, but apparently the idea is very simple, that you just need to sum the series for taking the dependence N of LD. Okay, I think I've done this computation, but I simply substituted N of LD in Mathematica and computed what is the sum, how it scales with L star. So it's some straightforward computation. You take an L and compute it with the power of L, and you get power L star D minus 1 over 2. And this will be substituting relation to S, it will be proportional to S to power 2 minus D minus 3 over 2 D minus 2. And for all dimensions higher than 4, it's less than a squared. So we are fine with this, and low spin part will not interfere with the analog of Martin-Froissart bound. It will still leave us safe with a squared bound. But apparently I will show that the part which is resummation of higher spins will bring a contribution which grows faster with S, unlike the case of Martin-Froissart bound derivation, where high spin part was exponentially suppressed. This is not the case of eikonal resummed graviton scattering through graviton. And my purpose is to show how this can be evaluated at all. What's the main contribution to this kind of integral? Well, I think I can make a couple of minutes break at this moment. Have 40 minutes left, right?
There is that first you go to the eikonal,
Yes.
then you go back to the amplitude from the eikonal.
Yes, kind of.
So that approximation, you have a resummation, many gravity exchanges.
Yes, exactly.
I know another formula which is not that one. In 4 dimension, it's much easier formula that I cannot connect.
You mean in 4 dimensions, if you simply
The Fourier transform should be done back with the
Yes.
exponential, not with the Bessel formula.
it can be done with exponential because Bessel function, sure. Because I will need the function Bessel function limit at large B, large argument, which is close to exponential. So basically, I will be using exponential. Then J0 is not, but it's Fourier transform in 4 dimensions is covered by a Bessel function if you come to impact parameter space. Exponential is if it's like full 4-dimensional Fourier transform. Exponential is for full 4-dimensional Fourier transform, but if you go to impact parameter representation, you get exactly Bessel functions in this case.
The idea is that you go to the eikonal with exponential. You go back to the amplitude with exponential minus. Instead, you will have something else.
It doesn't work like well. When I will be computing this eikonal, I will expand this exponential. I will expand this Bessel. I will use instead exponential. Yes, it will. I'll show. But in exactly 4 dimensions, if you close your eyes on the divergence, on the infrared divergence, you have to integrate. This integral can be very easily computed.
Neglect the divergent part, you take just
Yes, that's what people do sometimes. Yes, that's true.
go back to the
Yes, you can do it, and you cannot compute it analytically. I know this. Yes. I know this formula. I know the formula what you are having in mind, and I plan to mention it slightly. But because if I'm interested in analytic properties of the result, looking at the 12th formula, I'm getting confused because it's not a local, there is no Martin-Froissart bound, I would say. It's exponential form. It has an exponential form. At fixed t and large s, it will be something behaving exponentially.
exponential.
In s. If you take fixed t, it will be something like In big U, yes, but I mean, after taking the integral, after taking this resummation, you can obtain the result as a function, like new amplitude as a function of S and T. From the point of, yes.
But by kappa technology, they essentially compute, they go back to the amplitude from impact parameter space to the T space.
Yeah, in 4 dimensions, I said that you can compute it completely. It will you can get a result.
I don't see this formula in 4 dimensions. It's equivalent to the.
After taking the integral, it will be there should be Bessel function. If you are doing Fourier transform in impact parameter space, there should be Bessel function of 0 order. But you can you get just because of log of b, you delta 3 will have some log b form, and then you have to integrate Bessel function with b to some imaginary power. After this,
When impact parameter space, don't you use exponential?
No, but because I integrate already on the airports, right? I mean, there is the exponential of b product with q. Yes. But she has a one-dimensional integral there, db.
yes.
So basically, she has integrated on the angle the scalar product exponential.
Yes, exactly.
That's why there is a Bessel function.
There was
Back to not a one-dimensional integral, but to a d minus 2 dimensional integral, you will restore the exponential of b dot q.
So you mean that if you rewrite this as a D2,
yes. If it's D2b, you get back exactly. Okay, I think I can proceed. I plan to finish this computation. So even in d dimensions, this computation can be done with the use of the method, with the use of stationary phase approximation. And to perform this computation, I need large argument Bessel function expansion, which is root 2 over pi b q cosine of bq plus pi d minus 5 over 4. But instead of Bessel at large bq, I get cosine here, and I have the leading contribution will come when I have a stationary phase condition which includes this exponent and the exponent coming from cosine. So the stationary phase condition means that I need d over db of plus minus bq. I have exponent of plus of this and the exponent of minus of this inside cosine, plus delta 3 of b equal to 0. And I want to have this stationary point such that b is larger than b0, b star. If it is inside, then it's the leading contribution. So delta 3, I will write it like some constant alpha as b to power d minus 4 minus d. And for this reason, I get q minus d minus 4 alpha s b3 minus d equal to 0. And I prefer plus sign to get b b at least positive and being pretty large. So my stationary point b0 is q over d minus 4 alpha s to the power 1 over 3 minus d. So it is proportional to s, scales as s to power d minus 3. And recall that b star was s to power 1 over d minus 2. And this is larger. S to 1 over d minus 3 is usually larger than s over d minus 2. So I have this scale like b star, and b0 is larger in terms of b. I'm taking integral from b star to infinity, and the main contribution is got at the stationary phase point, which is equal to b0, and scales as s to power d minus 3. And then I can simply substitute stationary point expression and multiply it by additional root of 2 pi over this function of b0 double prime. Basically, this phase differentiated twice and taken at the point b0. So is everyone familiar with the stationary phase method? So I'm just doing it very sketchy, and after that one can simply substitute b0, collect all powers. It's kind of pretty annoying computation, but the result after collection of everything is that you get eikonal contribution to the amplitude proportional to exponent of I, some constant containing many factors, q to power 4 minus d over 3 minus d, s to power 1 over d minus 3. This is the factor standing in exponent, and here is the factor s to the power 2 minus d minus 4 over 2 d minus 3, and q to power d minus 2 squared over 2 3 minus d. Then I'm using like q to be fixed and take a limit of large S, and I notice that the scaling is s to power 2 minus d minus 4 over 2 d minus 3, which is in I mean, this power is larger than that power of lower spins, and apparently it is less than s to power 2. In starting from d equal to 4, we get less than s squared. Formally substituting d equal to 4, we get back s squared exactly, but that's kind of a bit more problematic, and the main problem is even not in this place that we are getting exactly s squared and taking limit of d equal to 4. The problem is living in this exponent. I especially left it as it can be obtained from the stationary point approximation. Apparently, we can see that if d is already if this power is quite small in large D. If d is equal to 5, I get s to power 1/2, and this is the maximal power. So the amplitude is behaving as exponent of I to the power s to power 1/2. But this means that everywhere in the first sheet of complex plane, this is suppressed. I mean, this is less than some constant, bounded by constant. It's not, it doesn't have growing directions. Exponent of root s doesn't have any growing directions. And this is good because after that we can conclude that our theory is kind of almost local, so polynomially bounded, and there is no problem arising because of even after this resummation. But in d equal to 4, we have, if we take formal limit of d equal to 4, we have some not so good things like exponent of I s to power, basically exponent of is. And this means that this function already the first sheet of complex plane will have a growing direction for imaginary part of s being negative. That's it. If imaginary part of s is negative, then this amplitude has a growth direction, and for this reason, in 4 dimensions, the eikonal resummation of GR amplitude leads to some non-local amplitude. The same can be obtained not by taking formal limit d equal to 4, but also taking omitting the infinity here and expanding the log. Even after that, it can be computed fully to some analytic result. But this doesn't help much anyway. It will have a form containing exponent of is and probably some log corrections to this s, and this doesn't help to close the contours and dispersion relations. That's my statement. But if d is larger than 5, we are safe to close the contour. So let me now comment a little bit on what to do if we have d equal to 4 and what can we obtain if we assume that still amplitude is bounded by s squared, d equal to 4. Amplitude of s is bounded by s squared, and the eikonal resummation is something which is for some reason not valid. We have to do something else. For example, match it to string amplitude, which has Ricci behavior. I'll mention it a bit later. But okay, maybe I can mention it now. Recall that string amplitude, which Ivano Bazil promised to derive during his lectures, it can be written in this form. I'll just take scalar scattering through graviton described in string theory. The expression is like this. That's the full expression for Virasoro-Shapiro amplitude. Then, if I'm interested in the limit s to infinity and t to 0, it is kind of pretty easy computation to make a series expansion in this limit, expand in s at infinity and in t when t goes to 0. And the result is s squared over t 1 plus 2t log s plus 2t squared log squared s plus some coefficient log s, which is subdominant compared to log squared of s, plus 4/3 t cube log squared s, log cube s, plus something log squared s, which is subdominant compared to log cube, and the leading again 2/3 t to 4 log to 4s plus this limit. So if one makes this exercise in Mathematica, probably it's pretty easy to do. One can see that we at each term in the T expansion, in T you can expand it in series. The leading term in S has a form of log to the same power as T, and the others are subleading. This structure is resembling so-called Ricci behavior, that it's S to power 2 minus alpha prime T over T. But this one is fine with it's less than a squared, and presumably we can use dispersion relation technique. It doesn't have any non-localities. So if we assume that it somehow gets matched to string amplitude, in principle, even in 4 dimensions, we can use dispersion relations. But if we can use dispersion relations, it also has certain implications. And one of the implications is a very funny connection between infrared amplitudes and ultraviolet amplitudes, which was in one of the Claudia's paper was called as reverse bootstrap. How can we do it? In low energy, anyway, amplitude has a form like a 0 s squared over t. I take the limit, find like small t. So I all u terms are coming to that. Plus some maybe loop correction. Plus other high loop corrections. But this can be computed if it's scalars exchange. Basically, it's this amplitude. One graviton loop, and this is scalar exchange through graviton. So that's the infrared structure of the amplitude. Then we can. Yeah.
The real expansion, the correct expansion is what you wrote there with alpha prime. I mean, you have Regge behavior.
Yes, I mean, you can derive it to expanding the amplitude. But I just wanted to show some special structure that you can obtain some certain coefficients, and you also have logs with lower power, but they will be subdominant in this limit.
That expression must be also alpha prime.
I think alpha prime is just like here.
But with the expansion there, 2t log s is not correct dimension.
Yes. I think that there should be alpha prime in each power of t.
So what you have done, you have taken s to the square over t exponential alpha t log s, and you have expanded. That's what you have done.
Yes, kind of. So this I'm just claiming that Ricci behavior can be obtained by expanding this amplitude into series. I will need this later. I will need this particular structure. It will be important for some conclusions. So let's remembering the dispersion relation technique for what I called C20, which is second derivative of the amplitude. From low energy theory, it's can be computed as twice differentiated by S amplitude. But we have another expression for this, and plus something finite when t goes to 0. It is equal to integral, as I've done it, like epsilon squared lambda squared to infinity of imaginary part of S and T over mu cube d mu will be in two imaginary parts here. So using results from the previous lecture, I can write it like this. Then accurately taking limit t going to 0, I notice that now I have divergent terms in the left-hand side. And since this dispersion relation is precise, if I throw away the infinite circle, I can now try to ask myself, where is this divergence in the right-hand side? Since here, if I assume that imaginary part is regular in t, so my assumption is imaginary part is as a function of t is regular at t going to 0, which is certainly the case of Ricci behavior. So there is an example like string amplitude which satisfies this condition that imaginary part of the amplitude is regular in t. After this, but I don't limit myself to string amplitudes only. I just take it as a general expansion and try to understand what does it mean for what does this relation actually mean. This relation, if this is regular, the only source of the divergence can come from mu dependence here. So it should be some infinite tail of the integral, which is converging when t is negative. When t is negative, non-zero, it's finite. But if t is going to 0, it's becoming divergent, such that it should be 1 over t divergence as a leading one. So in principle, I can guess one solution. I can treat it as an integral. I can treat this as integral equation on imaginary part dependence on mu. And I can present one solution, which is the simply Ricci form, like imaginary part of A is equal to S to 2 plus alpha t. This will work if I substitute it here. This will work and reproduce me the desired 1 over t behavior, but without log t, of course. How can I generalize this? So in principle, it could be not the only solution of integral equation, and I can add some function of S and t here and try to figure out how can I, what kind of form of this function can go through this equation. I can expand my function phi as 1 plus phi of S0 plus phi t of S0 t plus and so on. So I do Taylor expansion in t. And then I can also plug it to this equation and get that integral of 2 s to power 2 plus alpha t phi of s 0 plus phi t of S0 plus so on over not s but mu over mu cube d mu is equal to some infrared divergences of in graviton exchange or graviton loops in principle. Now my question is how to find these functions phi, phi t, and higher order functions. Is it possible? Apparently, it is because there is the following observation. If I do change of variables, mu equal to some scale m squared exponent of sigma, I get instead the very nice integral, which has exponent of minus sigma t sigma t because t is negative. And here I get phi of mu 0 plus phi t of mu 0 t plus so on. D mu, d sigma now. It is equal to f of t, which is divergent. Then if I'm hunting for divergent parts only, I can add any finite part, and in this way I can take the integral from 0 to infinity, and notice that I have nothing else but Laplace transform. Right? It looks familiar because phi of sigma 0 is integrated with an exponent, and I'm getting some function of t. So function of t, which resembles IR divergences like a0 over t plus a1 log t, is related through Laplace transform to correction to Ricci form of imaginary part of the amplitude. That's something we noticed. And this tells us how to find these corrections. So what is the general form of these corrections? And apparently I can find, using the table of Laplace transforms, I can find that phi of sigma 0 is inverse Laplace of f of t. Phi of phi t of sigma 0 is inverse Laplace of f of t over t. And this way I can restore the function. And for f of t equal to 1 over t, we can get that phi of sigma t is not actually a function. Phi of st is a function of only one argument, phi of t log s combination. So from very general grounds, just assuming regularity of imaginary part, we can find that 1 over t divergence dictates us that the imaginary part should be Ricci form multiplied by function of t log s combination only, not by something else, some additional terms separately. So this is the leading contribution to Ricci behavior. It should have form of function of combination t log s. So the Ricci limit in 4 dimensions is t log s being small. Then Ricci form is valid. This expression is valid when t log s is small value. To add dimensions, it's t over mp and also s over mp squared. This is the correct Ricci limit. And in this limit, amplitude as a whole can be just restored by analyticity, and it's well-known result. If we have Ricci behavior, we have a0, some exponent of minus I pi alpha t over sine pi alpha t s plus s to the power 2 plus alpha t plus u to power 2 plus alpha t. Plus maybe some corrections of t log s, of the form t log s. So we know in imaginary part we can restore the whole amplitude, which it's important to mention here that it's still, even after restoration, it is satisfying the condition that a of s is less than s squared. In addition, if we had log divergence from loops, we need to add correction 2 plus alpha t 1 plus 1 over log s. This will work to reproduce log t divergences at one loop. So this kind of relation can be used for predicting what is imaginary part of amplitude at large S, and then by unitarity we can restore the full amplitude and the Regia limit. So this is something that can be done for graviton scattering amplitude under the assumption that imaginary part has something close to Regia behavior. But basically, we need just assumption that imaginary part is regular in T. With eikonal resummation, it is not regular in T. Imaginary part, if after resummation, will not be regular. It can be checked. So there are two different assumptions living in these two ways of computing of high energy scattering through gravitons. So if we have this assumption, still we have problems to get positivity bounds on C to 0 coefficient. Why there is a problem? Basically, the problem was noticed when people were trying to compute one loop corrections to quantum electrodynamics with gravity. And for example, there was a
what you got at the end is what you should write up there if you do the correct Regia behavior of the amplitude. Is that what you? I mean, the Regia behavior of the amplitude you wrote there contain an imaginary part.
You mean this one?
No, the one you first line.
This one?
A of S of T, the ratio of 3 gamma and 3 beta.
Yes.
You do the expansion, you get an imaginary.
Yes. You get imaginary part?
The imaginary part that you will get there is the same that you got there or not?
Well, it can be, the form is the same, but coefficients can be different in this expansion. Because Regia part in string amplitude has certain coefficients here, but if I'm just starting from assumption that imaginary part is regular and do this technique, my coefficients can be arbitrary.
Because apparently the expression that you will get there will have a power minus I pi alpha prime T over 4, which is very similar to what you wrote there.
It's similar, but I'm saying that the leading term can be matched one to another, I guess.
The question is, do you get the same imaginary part that you get from string, or you get something different?
I have a possibility to get something different. At least at this stage, I don't have a contradiction.
Very stable, very stable.
Well, I mean, okay, I can state the result as the fact that I need just to assume that imaginary part is regular. It gives me Ricci behavior as a leading asymptotics, and some series in terms of T log S as a solution which reproduces me graviton pole properly. That's what I get. It is similar to what we can get from string amplitude directly, but in principle, no one says that I can this is a function, right? This series expansion is arbitrary and it goes through the equation. There is no problem for this. But string amplitude has certain coefficients here. So, well, I can say that coefficients here can be arbitrary, but of course, maybe I need to impose some partial wave unitarity in addition and get some bounds on them. But in general, at this stage, it's not obvious that it's like just a unique expansion. It's one. The form is very similar, but I'm not sure it will be, at the end, it will be unique. So let me briefly comment on the fate of positivity bounds, because it's somehow related to Ricci behavior and so on. So the story was that people were trying to compute QED with gravity, like electron and photon and graviton. And there is a diagram of this topology. And compute light by light scattering. Here is gravity. And here we get back photons. This kind of diagram behaves like minus gamma s squared. It has a term with negative sign. So I don't remember the coefficient. Let's say gamma e squared over m to 4. So m squared, m electron squared, and 1 over mp squared. There was a negative contribution standing in front of a squared, and there were like many discussions whether it contradicts to positivity or it doesn't contradict. So you simply need to compute this type diagram in low energy theory with graviton, and you get a negative s squared term. So it was, here are photons. Apparently, this term can be quite large because there is electron mass, and electron mass is electron is light. And how come that we have such a large negative contributions? Apparently, the story is that even if you have large negative contributions, you can hide them in subleading corrections to Ricci behavior. The point is that this, in the same way as I hide 1 over t pole, 1 over t pole gets hidden by something which corresponds to in imaginary part, it corresponds to s to 2 plus alpha t. But if it's 1 over t plus some constant, I can also get subleading. Simply put t c exponent of 2 plus alpha t. But this is subleading compared to 1 in the limit t going to 0. In principle, in this form, c can be arbitrary, even negative constant. You don't get any contradiction with this kind of form of the amplitude. And actually, due to the presence of graviton pole and precisely the form s squared over t, also plus s squared log t, you can hide everything into renormalization of log, which means that because of this particular structure of infrared divergences in gravity, we cannot have an argument for positivity conditions on a particular coefficient corresponding to c to 0. So gravity spoils positivity bounds for this coefficient because one can hide them into corrections, subleading corrections to Ricci behavior. And this happens, and it is known as a fact that light particles in the theory lead to significant corrections to Ricci behavior of at high energies. This is stated kind of as a well-known fact, and there is no contradiction between fundamental principles I discussed in the first lecture today and having large negative contribution to second derivative of the amplitude and the squared term. So this happens only for c to 0 term because higher order positivity bounds, they are still safe with this for the reason that if we take more derivatives in S, we stop having these divergences. They will just go away. So the system of Wilson coefficients can be bounded still without just the first of these bounds with gravity. That's the fate of first positivity bound, and historically first one derived when you consider theories with gravity. And here I finish my lectures. Thank you very much for your attention. Other questions? Yes.
I was confused about the last statement. So you derived the bound for C20, which was positive
Yes.
from general concentration.
Yes.
Then when you consider this for gravity plus
Yeah.
QED, you find that no, this is negative. But then you said, okay, this is not a problem.
Yeah, I was a bit quick on this, but apparently the problem with gravity is that there is in other theories without gravity you never get a squared with when you never get divergent dispersion relations in T to 0 limit. The problem is that second twice subtracted, as we say normally, or second dispersion relation corresponding to second derivative with respect to S apparently has a divergence. In principle, you just get 1 over t plus something, and t goes to 0. In principle, it just disappears. The bound is disappearing because left-hand side is going to 0, right-hand side is to infinity, right-hand side going to infinity. We're just trying to find something, locate something on the right-hand side which can reproduce 1 over t in order to get some bound or try to get some bound on what is left as a finite part of this dispersion relation. And finally, we found that it's not possible to locate this. Before that, there were statements in the literature that we can simply throw away this pole and use all these techniques, simply just like let's eliminate this pole and proceed using positivity bounds technique. Then this suggestion got contradiction with explicit results apparently for this amplitude. It looked very mysterious that you get pretty large negative coefficient. And there were even statements that QED with gravity needs UV completion at the scale root of mass electron mass Planck, which is pretty low scale. But apparently then there was an understanding that this is some the problem is reduced to the fact that we cannot justify twice subtracted dispersion relation if there is gravity. It's only with gravity we get divergence in this dispersion relation.
Is it correct to say that C0 bound does not apply to gravity? You have gravity.
Yes, strictly speaking, yes. People still apply, saying that gravity is suppressed somehow, or they also you can see in the literature statements like low spin domination, which literally means that you can simply throw away this pole and say that amplitude is dominated by the other contributions. Because as we saw from eikonal technique, that S squared over T is something which is high L dominated instead of low L domination. But in principle, you can assume whatever you want here.
Is that the piece which is like called as gravity amplitude being non-unitary? The unitarity problem, the high energy unitarity problem of gravity, is that the term?
I don't think it's there is a problem. I don't know actually what you mean.
There is a statement that amplitudes in gravity are not unitary at high energy.
What?
The amplitudes in gravity are not unitary at in the sense of high energy. The growth with high energy is minus unitarity.
It's more like perturbativity does not hold.
Yes.
Yes.
But literally, if you take
Yes.
I see. If you take GR amplitude, well, of course, there is some strange stuff happening when I do partial wave expansion of forward limit amplitude. But in principle, I can construct non-forward amplitudes, like simply exchanging, taking scattering of two different scalars through graviton. This kind of S-channel diagram, right? Different particles. There is no T-channel scattering in this case, but still it will behave like S over NP squared. And there is no possibility, I mean, if you compute partial waves of this, there will be some T proportional contributions, but no way to make them unitary for, so FL is proportional to this one. And of course, at some point, they should be less than 1, but it's not possible to have 4 energies higher than Planck mass. Yeah, they are becoming non-unitary, and one needs to do something with gravity, either resum or match to some string amplitude. And here I just reviewed 2 possibilities how what can be done with unitarization of gravity in some sense. More questions? Yes.
Many foundations. There are some branches.
Well, so far I think it's compatible, and there isn't like I don't think this technique can put some constraints. Well, up to the fact that, of course, string amplitude doesn't contain loop corrections to graviton scattering. For example, this amplitude does not match with what is needed to compensate log T divergence appearing at one loop.
It's a 3-level up.
Sure. You need, you need to improve string amplitude too to get loops. Sure. But I don't think it should be stated as a constraint. It's something like, well, you need to match to same level of perturbation theories. If you consider loops in one case, you need to consider loops in the other case. There are no miracles.
The analysis that you do there, the dimensional constant is the Planck mass.
I can use dimensional constant as a Planck mass.
You cannot write the sum of the 2 terms like that. You must introduce a dimensional constant.
Yes, of course.
Which is the dimension? It's the Planck mass in your case.
You mean here? Yes, Planck mass. Well, it depends on what kind of matter you consider. There will be some, I don't know, some coefficient, some number, depending on what kind of particles you scatter.
It's totally different in the string. Because in the string is alpha prime, it's not a Planck prime.
But alpha prime, in principle, the fact is that this alpha cannot be, if I remember correctly, our result, alpha is some arbitrary parameter. We cannot constrain it from low energy theory. It gets cancelled.
Alpha is alpha prime, actually it's divided by 2.
Yeah. In string theory, it can be not obligatory Planck mass, of course. In string theory, it can be not a Planck mass.
Not the
Yes, I know. But you have also some constant in front, which should know something about Planck mass. I would say the technique of matching Ricci behavior to infrared singularities, it doesn't predict what is alpha in this amplitude. You can get these results for different alphas. We don't have prediction.
Yeah, but you must tell what is the physical quantity alpha. What is
At this moment, it's arbitrary, but in principle, one can put some more constraints like partial waves, partial wave unitarity. Then there will be some relations, bounds on alpha.
in a gravity theory? The only dimensional constant is Planck mass. What else can you use?
Well, there are numbers: Planck mass multiplied by 10, Planck mass divided by 10. In principle, if I do partial wave unitarity, probably I get some bound on alpha compared to Planck mass. That's what I assume. I need to check. Apparently, it was claimed to be done in the recent work, but I don't remember if they got some.
I guess the string amplitude will pass all your tests.
So far, yes, it should. Well, except for they need to get loop correction there. Yeah, three-level amplitude will not pass the test matching to loop graviton.
But that is a 3-level state.
Yes, sure. I mean that depends what of course for checking and passing all the tests. In principle, you need full like all loop amplitude from string theory. Testing just 3-level is maybe a good thing, but depends on what's the size of loop corrections.
Doing the barbecue because
Yeah,
start preparing.
I guess people are hungry. Okay.